I decided asking it once was not enough. So I asked the question again. But I figured it wouldn't be too hard the second time, since the second question is almost the same as the first question, except I threw in a little wrench to make you think a little bit. And yes, you should be able to handle such things as this. Just fixed the instant bug on my test. Okay, given a univariate nonlinear model, what does univariate mean? It means there's only one variable, in this case x. It implies that x is not a vector. In the real world, it's always a vector, so you'll never deal with univariate models. But, well, I say that. The assignment you're working on right now is univariate, isn't it? Okay, well, there you go. It means there's only one x. It doesn't mean there's only one parameter. There are two parameters, m and b, and here it is. This is a nonlinear model because it has an f in it, and what is f? Who knows? Presumably it's some nonlinear activation function. And the objective function, and then I threw in a new objective function. What's that going to do to you? Just changes what you have to differentiate. If you present the training pattern, basically everything else is the same. And by the way, f of x, or the derivative of f of x, can be expressed as f prime of x. That's just there because you're going to need it. So let's solve this same problem again, and I don't feel bad doing it again because, once again, this is pretty much the main thing I want you to get out of this class. That's not true at all. I want you to get all kinds of things out of this class. But if you don't get this, you missed what it's all built on. And so I will make sure you get this. I'll make sure of it by scaring you into believing that this question will be on the test. And the best way to do that is to actually put it on the test. So be aware, the final is coming. Okay. Here's my new objective function. And let's suppose I want to update the weights of my model. What do? Well, I need to compute the gradient of this error function with respect to the weights of my model. So can I save a little time by coming over here and saying that's what I want? And that happens to be equal to the partial of, in this case, I have an absolute value. Ew. Right? Sorry, I hate it when people use absolute values on tests because it means you have to do the darn thing twice. So not only did you do it once and then a second time, now it forks into two, and now you have to solve it a third time. So yeah, basically there's going to be two cases. There's the one case where this is negative and the one case where this is positive, and that's the only way to deal with an absolute value. So let's make an assumption. Assume y sub I minus h of x sub I. Or let's assume it's greater than. And then we'll do the less than case next, and there you go. If we make that assumption, then the absolute value just goes away, and life becomes super easy because now we're just doing y sub I minus h of x sub I. Right. So now, how am I going to get, I forgot something. Yes, I didn't forget something. That thing I forgot is it was the f, you're right, but it's actually inside of the h. So we're good. Moving on. That is equal to negative this partial of h of x sub I. Is it not? I just pulled the minus out in front and I dropped the y sub I because changing our weights, whether it be the m or the b, is not going to affect some label. But it certainly will affect the hypothesis because the hypothesis is built on m and b. So there we go. Why am I getting bad feelings about this? Oh, that's because I did it differently on the key. Doesn't matter. I'll just keep going. As long as you do it right, doesn't matter how you do it. So, partial with respect, okay. What do we do next? Help me out. Okay. I didn't hear anybody say expand h, but that's the answer. So we're going to expand h because that's the only way to push that partial derivative through. And what was h? F of mx plus b. So f of mx plus b. It's equal to that, which is equal to negative. Now, how do you differentiate f? What do we do? Again, we're going to use the chain rule, and there's a hint right here. The derivative of f can be expressed as f prime of x. Well, the derivative of that simply reduces to f prime of mx plus b. And I have a problem because it used an intelligent quotation mark, and I need a dumb quotation mark, so I have to copy it and paste it so it doesn't throw off my LaTeX editor. There you go. Okay. But I'm not done because the chain rule says to take the derivative of some function, you take its derivative and then multiply by the derivative of what's on the inside. So I'm going to take this and put here a mx plus b. Okay? You see why I did that? Essentially, I pushed that partial derivative with respect to w through that function by turning that function into its derivative, and then I multiply by the derivative of the inside. You see how that's the chain rule? It is the chain rule anyway, so if you have forgotten your calculus, this is your refresher. Welcome back to calculus. Now, what is the partial derivative of, well, we're going to do it with m and we're going to do it with b. So if w means m, what's the partial derivative with respect to m of mx plus b? It's x. And in the other case, what is it with respect to b? 1. And now let me come over here and still these things so I can make a mental note of what we've actually done here. Here are our two gradients. We have a gradient of our error function with respect to m and a gradient of our error function with respect to b. And if we want to improve our model, which we do, we want to subtract these gradients from them. So we're going to say m is equal to m plus eta times this whole thing, and I'm not including the minus sign because I did a plus there instead of a minus. And I'm going to say b is equal to b plus, I'm just going to copy my eta, that thing. I don't actually need those parentheses, do I? Because the f covers me. So this is the answer to this problem for the positive case, meaning if I assume that y is more than h of x, as long as that's true, then this is how I update my m and my b. Now what we have to do to complete the problem is make the opposite assumption. Y jipes. Y sub I is less than h of x sub I. Boom, 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 boom. Okay. Now this would be a nasty problem, except we've already done it before, and now we're just going to go through and fix all the stuff. So, paste. Don't you wish you could copy and paste on a test? It would be so nice, but you can't. Okay, if this is the case, then the partial derivative is going to be negative that, right? Because now we're assuming that it's the inverse. Or you could switch the h of x and the y sub I, or you could put a minus there and a plus there, however you want to turn it around, but either it all works out the same no matter how you do it because it's math. Okay, which means that, what's that going to do? Well, that minus is just going to go away, isn't it? That is the only thing that's going to happen. Well, that's easy. That means that minus sign is going to go away, and that one's going to go away, and that one's going to go away, and that one's going to go away, which means this one's going to turn into a minus. And this is what you do in the case of that one. And if you want to rewrite this in some fancy way, like take y minus h of x divided by the absolute value of y minus h of x, which works out to the sign on that thing, and then put it in front of this so that you get one equation that expresses the thing to do, that would be awesome, but you don't have to do that. Anyway, if you got some form of this, that was the answer and you nailed it.
Do you have to include the 0 case even though it's just 0?
See, what is that? The absolute value of 0 is 0, so I claim it works out to the same number in both cases. Therefore, no. Yep. I'd like to think of 0 as being positive. In reality, I guess there's a negative 0, isn't there? I don't know, depends on the machine, the architecture. But the answer to your question is no. Okay. Next question. Please briefly identify 3 ways to limit overfit with a neural network. You see what I'm doing here? You know how I promise you I'm going to repeat questions so that you have to go study the questions that come up on your previous midterms? This is me making good on that and thereby providing evidence to you that you should take me seriously when I tell you to go study your midterms before you take the final. Okay. So, of course, there are not just 3, there are many. So let's just name a few ways to limit overfit with a neural network. There is, of course, early stopping, because you can't overfit if overfit happens from training for too long, right? Well, you can, but you won't overfit as much. The sooner you stop, the less overfit you get. Of course, you'll also destroy your training. So I don't like that solution, but it is one. The one I really like is get more data. I'm putting that as number 1 because when possible, that is the right answer. You should always do that one. Early stopping is another solution. There is also limit the topology. In fact, I like that one better than early stopping, so I'm going to promote them in order of awesomeness. And, whoa, whoops, wrong button. Here's regularization. L1, L2, max norm, any type of drop out, drop connect, any type of regularization you know would be fine. Regularization is a good way to make a neural network simpler and is probably better than these other approaches. Are there any others that you thought of that I didn't? I think those are the only ones that came up. Yeah. What was that? Shuffle the training data. Got to think about that one for a second. That one, huh? You're right. You should shuffle the training data. Does that prevent overfit? If you don't shuffle the training data, you'll overfit to some of the patterns in the training data, which I guess is overfit. And the more I think about it, I think somebody put that on the test, and I didn't give credit to that. And now that you're saying it, I'm thinking it's technically right, although I don't think it's a great answer. Here's why I don't think it's a great answer is because usually overfit, if you're overfitting, basically you always shuffle your training data, and by overfit, I kind of mean after you shuffled your training data. It's a technically right answer though, so if you're the person that put that, you probably want to come talk to me and I'll give you some points. There you go. Next one, number 10. Given a one-dimensional input image with 4 elements and a filter with 3 elements, please give 2 expressions for the 2 output values that would be obtained by convolving x with w. You may assume there's no bias term. In a convolutional layer, there will always be a bias term. I'm just saying let's drop it because it makes life simpler. So here's what I'm giving myself some more space to work with here. Okay, we have x1, x2, x3, and x4, right? And we're going to convolve that with w1, w2, and w3. Well, that's going to basically lead to x1, w1 plus x2, w2 plus x3. Wait, I'm not writing this correctly. x2, w2 plus x3, w3. Let's techify that, comma. Then this kernel or filter is going to slide over, and we're going to get x2 w1 plus x3 w2 plus x4 w3, which looks like that. And that's it. Right? Give two expressions for the two output values. Okay, I guess I should have put it this way then, so that I can answer the question correctly. y1 equals that. y2 equals that. There. I have now given two expressions for the output of convolving this input with that filter. And there was the expected answer. Any questions on that one?